Hello. I think we're about ready to get started. Thank you guys all so much for coming out today. This is Constexpr, All the Things in Audio Programming. This title, as well as a lot of the ideas and like concepts that it builds upon, were from a talk in CPPCon 2017 by Ben Dean and Jason Turner. This talk was sort of remixed and done a few other times, and referenced in other talks. So this one is not the first one to build on these ideas. And a lot has changed in C++ since 2017. So there's a lot more to work with and how it pertains to audio programming specifically. My name is Adam Shield. I work for Antares, best known for Autotune. And we have a whole suite of vocal effects. I develop audio plugins there. But my title is also DevOps engineer. And so in addition to working on individual audio plugins, I spend a lot of time thinking about the big picture, how all these different plugins fit together, shared code, sort of like the whole ecosystem of how everything works together. And in doing so, I have sort of the opportunity to do some experimenting, figure out, for example, what are the best ways to do automated testing and stuff like that for our code base. And so the genesis for this talk sort of comes from one of those experiments. Just a quick note about some of the slides. I made these sort of little different indications for the different languages, or the different versions of C++. So in the top right corner, whenever I'm showing code, it'll show like what version of C++ is required. C++ 98 is sort of a catch-all for anything before C++ 11. So really, it's pretty much anything before C++ 11. But then that way, quickly at a glance, you know what is required, because there's going to be a lot of code, a lot of snippets. So felt that was important. Quick note about the goals of this talk. We're sort of going to put Constexpr and compile time programming in C++ at large into context. So we're going to kind of move through the history, learn some of its benefits, and not to bury the lead, some of those benefits are anything you do at compile time is work that doesn't have to be done at runtime. So that's always good. And code that is compile time friendly or done in a constant context is it cannot have undefined behavior. So for free, you sort of get an undefined behavior check. Better practices such as you're encouraged to write pure functions, code that doesn't depend on global state. And then in this talk, we'll get to how you can run automated tests on that code at compile time. But there are a lot of pitfalls in writing the code this way, so we will definitely talk about that. But then in part two, we'll build on all of that foundation of Constexpr and how you can apply it to unit tests and DSP regression tests. So quick note, why am I talking about proprietary DSP code specifically? And this talk, a lot of what we're talking about can just apply to lots of places in your code base. I'm sort of singling out DSP just because this is an audio developer conference, but also I think it just kind of fits into this model really perfectly, or it did in our code base at Antares. The key word is proprietary. So what I mean is we're talking about code that is your company's code. So I'm not talking about you've included some sort of audio effect from a library or something like that. This is your own company's code, so there might not be any dependencies. It's often modularized from the rest of the code base. Because it is self-contained, it's easier to treat it separately, automate test it better, or separately. This also will address some linker issues that we'll get to later, so we'll come back to that. And very often, it's just simple C++. I mean, we're talking about DSP here, but we're talking about, lots of math, a lot of tables full of data, not necessarily too much other stuff required besides that. If you do use any of the STL algorithms, you're probably going to be okay, but we'll get to all of that. So, putting Constexpr into context. Basically, in the dinosaur age before C++ 11, we all know macros, we all know hash define, that if you needed some kind of global variable, you might do it this way. You might say, number frequency bands is 6. But macros have a lot of problems. They forfeit the benefits of C++. They don't have any type safety. There's sort of a pre-compile stage find and replace. So the types that they apply to are sort of come later. So they kind of lose the whole point of C++. The error messages, especially if the macros become really long or complicated, it might be hard to understand what the error is telling you because you have to kind of like look back at the macro and not look at the code you're actually looking at. What I think is the biggest problem with them is that they cannot be limited to a language-defined scope. So yes, you can hash define something and undefine it at a certain point later, but you can't just apply it to, say, a class, or you can't put it inside a namespace and then just have it apply to that namespace, or even just a function, or like just brackets. Sorry about that. But C++11 fixed that with the Constexpr specifier. So Constexpr declares that it is possible to evaluate the value of the function or variable at compile time. And I'll just highlight a few more things from the CPP reference. A Constexpr specifier used in the object declaration implies const, and that a specifier used on a function implicitly implies inline. So that'll come up later. That'll be important later. So now with C++11, rather than hash defining things, you can actually have a compile time known variable, but just marked Constexpr. So now it's known at compile time. Now I put it in a namespace. So it's separation of concerns. The data is inside an abstraction. We've already improved things. We are now writing C++. We can have a Constexpr function. So this function could be used at compile time to determine the value of another variable that is also known at compile time. But one thing to note, though, is that everything inside a Constexpr function must itself be Constexpr in order for it to be Constexpr. So that's an important thing to keep in mind. But C++11 was very limited. I should point this out. So even with just this function, you couldn't have like a variable at all. Like you had to just return the answer. It was a one-line function. So you were kind of writing a lot of like ternary operators, this kind of thing, were like nested ternary operators. Wasn't the most flexible. They fixed that in C++14 though. So then you could have variables and you could call multiple functions and do all kinds of logic inside a Constexpr function. I should note, we're still on C++11 here. It wasn't just integers. There's many other data types that were allowed to be Constexpr. Different integer widths and floating point values. You could even do pointer types and const char star. You could do standard array was available at compile time. References. Note that you're getting the const ref of a variable inside that array. And that's all fine. Function pointers, all available as of C++11. C++14 added Constexpr lambdas. So now the code's getting a lot more flexible. You can write more expressive code. As of C++17, a lot of people don't know this, lambdas are now implicitly Constexpr automatically if they can be. So as long as they're not doing anything that would not be okay at compile time, for example, like this lambda is trying to capture the the address of this more global type variable, that's not going to work in a Constexpr context. So that wouldn't work. Another tool at C++17, we're sort of getting more and more esoteric here, Constexpr if. So in this code here, we're going to call it here, I don't know if you can see that down there, with the type double. So as we move through this template, it is not an integral value, but it is is same as double. So only the code that is inside this branch will compile. So the other code won't compile. You can test this in Compiler Explorer and see that there is no assembly for the other branches. It'll just compile just that. So that's kind of useful in template programming. One thing that is kind of interesting that you can do with this is you can combine that with, like right here I have a return type of type T, the template type. But in C++20, you can actually return auto. So if only the code inside a branch is compiling, you could return different types for each branch, maybe not even T, and it won't matter. And like in that'll combine. This will compile just fine with C++20. This is a tool we'll actually use a lot later on in the talk. This is stood is constant evaluated. So basically, you can ask the question, is this code currently running at compile time, or is it running at runtime? And you could have different behavior depending on that. So this is a very useful, straightforward tool, but again, requires C++20. C++20 also added not quite all the algorithms, but virtually all of them, like all of the ones that I've ever needed. I couldn't even find one that they didn't add that are allowed to be done at compile time. So note, they also added standard vector. So now you could do stood sort, stood reverse, accumulate, stood fill. So many different algorithms are all available at compile time now. So looking forward, looking ahead at C++23, as of the making of this slide, these are all papers submitted for C++23, but none of them have actually been accepted. So if you're watching this in the future, this might not matter at all. This might not be true, but these are proposals for C++23 where they're trying to add a unique pointer. So as of C++20, you could write new and delete. So they actually have dynamic allocation at compile time now, but not unique pointer. So if you do Constexpr all your things, you will unfortunately have to write new and delete and not use unique pointers as of today. And there is no Constexpr in CMath. So that's a little bit frustrating. So you can't do like stood floor or stood pow, to get to the power of something. But we will address that in a later slide. And evidently, they're also adding optional and variant. So let's take a moment and talk about some of those pitfalls. So we have this class here. Let's say we have it broken up into our traditional header CPP file. We have an EQ class. We have this function here, get number of EQ bands. It seems really simple, straightforward. It's a pure function. It's not referencing any global state. It looks straightforward. I should be able to just add Constexpr to it, right? If we're going to Constexpr all the things, we can start with this function, right? But that will not work. And for some of you, maybe it's obvious. Maybe it's not obvious for some of you. But the problem with this is that link time is after compile time. So if you compile something in a CPP file, but it's not known at that compile time to other translation units, then those translation units don't know what it is. They can't, this just doesn't work, So the header file CPP paradigm doesn't work out of the box. If you Google this problem, they'll just say you can't do this. You have to write all your Constexpr functions in a header file. But there actually is a way around this. Basically, again, if you're writing library code, you might organize all your library code to be included in a single header. So if all of your headers in that library code are included in one header that you include in your elsewhere, then you can include all of the .h files and then all of the .cpp files right then and there. The fact that they are implicitly inline makes this possible. That top-level header could become a custom juice module. That's what we do at Antares. We just have that header, we just make it a juice module. Just kind of, fits right into our code, whatever plugin we need to use that code. We could use a C++20 module, although I've never actually gotten that to work yet. If you do, please come talk to me. So this is sort of what I'm talking about. You might just have all your header files and all your CPP files. This, again, sort of requires that you buy into the whole thing, though. Like, everything in these CPP files would need to be Constexpr in order for this to work. Otherwise, you'll have multiple definitions for the same functions in every translation unit. So sort of all or nothing with this particular model. Another pitfall you might run into is, OK, so I'm writing library code, but I feel a little weird. Like, it's OK for maybe our purposes to just say it requires C++20, but I just feel uncomfortable saying the library is now only compatible with C++20, so you might want to make it conditionally Constexpr if the tools that you're using require C++20. So just an example, it might look something like this. You might check if you have C++20 available, and then use that macro to sort of wrap the Constexpr specifier in your own macro. and then just use that wherever you need C++20. As I said earlier, the math functions, the CMath functions, are not available at compile time. So what we use is GCEM. It's just a C++ compile time math library. It's compatible with C++11. So you shouldn't have any problems with it. So none of those functions will compile: std, abs, pal, square root, round, sign. None of those will compile at all even today, but they will compile with GCEM. You just replace standard std with GCEM and use that library, and you're good to go. Atomics, we know, are like the one gold standard thread-safe solution for real-time processing. And so there's no way around it. You know, our DSP code is inherently multi-threaded. We have to change some stuff like in one thread and have it affect what is happening on the audio thread. So we know that atomics are the best way to do that. Atomics, of course, are not Constexpr. There is no such thing as threads in this context at compile time. So we're in a situation where we have to use atomics, but we can't. So I can just tell you what my solution was, and hopefully it's helpful to you. Basically, what I would suggest for a situation like this is to create a wrapper around it. So we have this Atari's atomic class that sort of wraps the atomic. And so basically we have the atomic version of the type that we're talking about and the non-atomic version. The atomic version we know can be used at runtime. The non-atomic version can be used at compile time. And then basically in the you can just overload the functions that you need, and you can say, if it's we used to constant evaluated, which we talked about earlier. If it's compiled, or if it's running at compile time, use the non-atomic version. Else use the atomic version. So there's a few more examples of that. Different operators, operator, multiply, et cetera. So now we're getting in the weeds here. I think we're not supposed to lock on the audio thread. We know that. I'm sort of including this in case you want to apply this same logic outside of the audio code, or in case you do lock like some small part of your audio code, maybe switching out something in an array or something. So I just felt I'd include this, but we are getting a little bit in the weeds. So my solution for this, I couldn't just declare the mutex inside this wrapper. I had to make it dynamically allocated. They were not trivially default constructible at compile time. So basically, if it's constant evaluated, or rather, if it's not constant evaluated, dynamically allocate and deallocate it. And then this is the wrapper for the lock, for the std lock guard that we used. Again, it's dynamically allocated. So if you try to do this in the audio thread, you'd have a problem. So now you're not only locking the audio thread, but now we're dynamically allocating on the heap on the audio thread, and that's definitely not okay. So just one quick solution, again, if you're forced to do this, is you could pre-allocate the memory using placement new. Basically just, for those who don't know, whenever you write new, you can provide an optional, you can provide an optional argument for the memory that you want to use. And you can pre-allocate the memory of the right size. All right, so I think that's enough putting Constexpr into context, and now we can apply it to our DSP code and our automated tests that we sort of talked about earlier. Starting with compile time unit tests, this is extremely easy, actually. Now, once we've made a function, Constexpr, we can simply use static assert, and right there we have a unit test. We can assert the behavior of the function, just like that. We can say that the function, or that 1 squared is 1, 10 squared is 100. And if anything, if we ever refactor this code and that is no longer the case, the code will not compile because the static assert will prevent it from compiling. Another thing to keep in mind also is now that we've used static assert, square is now forced to run at compile time. One of the things I should have said earlier is that Constexpr means it can be run at compile time, but it doesn't have to be. So if you never actually use it at compile time, you might not know that there's even a problem with it. So now that I've done static assert, if it definitely confirms this function has to be runnable at compile time. So sometimes you might be able to get away with writing Constexpr, but until you actually try to use it, you might not actually get a certain error. You could expand this further by using an immediately evoked lambda inside the static assert. So you can write more complex logic that way, more complicated unit tests. Here I'm writing unit tests for the Antares atomic that we talked about earlier. So just confirming that adding, subtracting, all of these things work with that atomic wrapper. Although it might be obvious, again, to some that like we sort of are now wrapping, or we're sort of pushing ourselves in a corner here. We sort of have a problem where we have two different behaviors. We have the compile time behavior and the runtime behavior of that wrapper. So we would need to actually test both of them. So one thing that you could do, instead of static assert, you could create a wrapper for static assert to confirm that the behavior works correctly both at compile time and runtime. Here's my solution for that, just a few lines of code. Basically, I replaced the static asserts with a macro, Antares assert, and that does the static assert, but then it also inlines this looks like little struct that takes the expression and runs it, and then you can, like I said, you could replace all your static asserts with that. If there's two different behaviors you need to check. Okay, so compile time unit tests are great because they don't require any configuration pipeline dependencies. You don't have to set up catch2 or gtest or anything like that. You just use raw C++ to test your code. You know, to fail a test is to fail compilation. You can't even compile the code on your own machine if the code isn't, you know, doesn't pass your tests. And as I said earlier, you cannot have undefined behavior in a Constexpr context. So if you write a memory leak, this won't compile. If you try to access code outside of an array, the compiler sees right through that. It can see the end of the function and know that you're trying to do something that is bad. And in that sense, Constexpr C++ is a lot like Rust if you write it this way. So I hope that's okay to say. Then, you know, I couldn't get it out of my head. I had trouble sleeping because I couldn't stop thinking about like, well, if everything is Constexpr, and we have these unit tests on these functions, couldn't I process audio at compile time, and then couldn't I know if I screwed up the audio when I do a refactor? I couldn't get that out of my head, so I did the work to make that happen. I'm going to show you how we can do some compile time DSP regression tests. So first of all, as we said before, all of those DSP functions would need to be available at compile time. And then we have to establish like the before state of whatever short little audio blip you're trying to test. So at Antares, we use this little recording of Somewhere Over the Rainbow of someone singing it kind of off key to test to make sure that our auto-tune is working. And so I just took, first I took the first 5 seconds of that, but that was way too long, and the compiler didn't like that, and it took forever to compile. So if you just make it, made it 1/10 of a second. That's probably still too long. But just basically, I don't want to show the code here, but I just made some functions that just took that WAV file and then just exported a file of the floats just in an array that then I can include that inside inside my testing code. And then I just need to have that before state in one file, and then I need to do some type of processing to it with the DSP object with certain parameters, set up however we want, and then be able to use them for comparison. So on the left-hand side we have the original audio. On the right-hand side we have it subjected to some processing. So the process function was called with certain parameters set up beforehand, and this is the output. And so now in our code, we can do that same test in a function that is statically asserted, and then check, is it still that? Is it still what is on the right-hand side? So here's what that function for us started to look like. We have assert compile time regression. So the static assert, I don't know if you can see it down there, calls the function. This is a new specifier we haven't talked about yet. This is consteval. It's the same thing as Constexpr. It's just only available at compile time, so you can't run this function at runtime. So then first line here, we run that test. We run that same DSP test on the audio with the same parameters set up and everything, and return the new process DSP. And then we just compare every sample of that to the one that we had saved earlier in that file, just to make sure that nothing has broken. And that did not work, actually. So I was really puzzled. I spent a lot of time on this. I assumed that I did something wrong, and I just kept going over and over it, and I was logging things, and I could not figure out why this was not working, that no matter what, it always failed. It always said something has changed from before, and I was trying to figure out what changed. Eventually, I don't know how I found it, but I realized that it wasn't guaranteed. The math of the floating point calculations was not guaranteed to be the same at compile time as runtime. So this is from the C++ standard. It says, since this document imposes no restrictions on the accuracy of floating point operations, it is unspecified whether the evaluation of a floating point expression during translation yields the same result as the evaluation of the same expression during program execution. So it's a little bit of a problem. I'm like, okay, so we don't know if the floating point math is going to be the same. I found this, actually in, just for reference, from a C++23 proposal, where they actually show that on some of these math functions. They actually show like where the errors occur. So that's interesting. Something's wrong with log 2. But anyway, okay, so what I found was that if you just have like a threshold for error, like a margin of error, and I just tried different values, and I tried to see how low I could go before I caught like that there was a difference. I went all the way down to minus 96 dB, and then everything worked after that. So the differences, from what I could tell, from what I read online, was that it was like a 1-bit rounding difference that we're talking about here. So evidently, minus 96 comes from the fact that that's the lowest possible value at 16-bit wave files. So that's where that number comes from. And that seems good enough for our purposes here for the testing. If we just confirm that the difference between the new process DSP and the sample from our saved process DSP, if that difference isn't greater than that little margin of error, then we know we haven't screwed anything up. So now in our code, if I try to refactor something and I accidentally don't paste something right, or if I just, I don't know, accidentally add a 1 at the end of a long float or something, immediately my Xcode is screaming at me saying that this won't compile, there's a problem because this static assert fails, and it's because I changed the DSP. So that's super useful. Again, catches undefined behavior right out of the gate. It turned out we had undefined behavior in our code since the early 2000s. There was like pointer arithmetic happening on uninitialized pointers that were fine because they didn't end up having, we shipped it, but it's still bad to have that, and it was really great that, we have this kind of test to just confirm and be able to sleep at night knowing that we do not have undefined behavior in our DSP code and that we have not broken it with any recent changes. Just a few quick resources I just wanted to list here, mostly YouTube videos that I really like that have to do with Constexpr. There's one here about how you can write a Constexpr random number generator, so if your DSP code requires that. There's a link to GCEM, that compile time math library that I said earlier. But yeah, that's Constexpr, all the things in audio programming. Thank you. Are there any questions?
Yes, there are a couple from the live stream here. Paolo asks, when do you prefer using Constexpr over inline?
I guess I sort of see them as different things. Again, Constexpr implies inline, so it is inlined. But Constexpr, for me, I get all of those other benefits that we talked about. Have no undefined behavior. It forces you to not write code that has like all these like global state stuff going on. Like the function needs to be pure. If it depends on a global variable, that global variable must itself be constant. So I guess Constexpr just gives you way more than inline, is just the short answer.
Excellent. And Mark asks, what is the debugging experience like when moving as much as possible to compile time?
For me, it's fast. I mean, like I said, anytime I make a change now in the DSP code, or at least I spend most of my time using Xcode, so your mileage may vary depending on your IDE. But it's really fast at telling me that, oh, hey, there's a problem. But I will say, though, that you can't step through the code at compile time the same way that you would at runtime. So that is definitely limiting. You still can, of course, run it at runtime and step through the code. But when I was trying to set all this up, that was a barrier, I will say, is trying to figure out, okay, something isn't working, but I don't know why. And evidently, there are ways you can kind of report what's going on during compile time, but it gets a little complicated. So there are challenges with that, yeah, for sure.
Hi, nice presentation. I'm curious about the compilation time after porting almost all your tests to Constexpr. So did you see any effect?
I will say I didn't notice any difference until I sort of hinted at it earlier with the that I used 5 seconds of that audio file. All of a sudden, it just kind of sat there and took forever to compile. And then I think sometimes I even got like errors and it just like wouldn't compile. Or it would say like, there's just too much math going on at compile time with 5 seconds worth of samples. That again, there was like it told me that if I added a flag that I could expand how much I'm allowing the compiler to do at compile time. But instead of adding that flag, I just used less. I mean, if the first several thousand samples, I should be able to catch, whatever is going on. I don't really need 5 seconds. But yeah, that was the biggest thing, was trying to add a big long audio file like that. So I would recommend not doing too many audio files and to keep them short. But then it's fine, at least for me. Mm-hmm.
Hiya. Are you still doing runtime unit testing, or have you given that? Is all your unit tests just done Constexpr now?
So this code is sort of, the code that I'm talking about here at Antares is sort of in the process of being refactored and pulled out of other like sort of legacy places and kind of all put together in the same place. So we're sort of adding testing to this collection of DSP for the first time, just because now it's all together and such and refactored and using the same shared code. So there is no other unit, or there is no runtime testing right now. But since, there was that one slide about how you can do both using the same macro, and so that's one potential use case. But yeah, I mean, I think at the end of the day, it's sort of up to you and your company and decide what's right for you. Maybe this just doesn't work for you in your code base, and that's totally fine. Or maybe you can use it in some places. But yeah, I think it just depends on your specific setup, what you think is best.
There's another one here from the stream. Powell asks, can Constexpr cause a decrease in code performance?
I strongly feel no. I don't think so, no. I mean, I can't prove that right now, but I don't believe so, no.
Hi, thank you for the presentation. Are there any possible issues that could happen with code bloating, the size of the binary increasing too much because of too many code being compiled? And if you use like same instance of some class, different input arguments or whatever, you end up with too many code being generated.
Oh, what was the first thing, the very first sentence you said?
The code bloating issue.
Yeah.
Is it possible at all?
I haven't experienced that myself. So, I mean, again, your mileage may vary, but when you say code bloat, are you referring to like the actual writing of the code or like the binary size?
The binary size, yeah.
Oh, yeah. I really don't know. I did not do an A/B comparison of the binary size. But it's my understanding that with Constexpr, you're giving the compiler more opportunity to optimize, not less. So if anything, the binary I would really expect to be smaller. I mean, like I said, there are these other talks that before this one that that go into, the benefits of Constexpr, and that basically you should just make all of your code as Constexpr as possible. So I do believe that the binary should be smaller, but I never actually A/B'd them to say for certain.
Daniel on the stream asks, is the compilation time longer for debug builds when running tests at compile time?
No, I have not experienced that. Like I said, if you're doing the DSP regression test and the audio is too long, then yes, there is it definitely takes longer. It's noticeably longer, but as long as it's not that long, then I have not noticed any problems with that.
Hi. You mentioned a barrier in debugging, so to say, because you cannot step through the code. And you mentioned that you found a way around when doing this. I would be interested in what your approach was to. Yeah.
I really didn't find a way around it. I mean, online, there were these ways that you could, I can't really, somehow you could use templates in the code to then output, there'll be an error message from the template not compiling, and then that can tell you what is happening. So you can kind of hack using templates to tell you about what's happening inside the code. I never actually did that, but evidently it is possible to do that. So that could be a solution for debugging at compile time, yeah.
James, over on the stream, asks, if you're processing audio that's only known at runtime, how much of your DSP chain can actually be computed at compile time?
I guess I'm not sure I understand the question. Because, yeah, you don't know what the audio is that you're going to get, true, but you could use example audio. You could confirm that, given a certain audio source and its processed result, that doesn't break after any changes that you've made. So I guess one thing you could do is have a little suite of tests, or not, maybe not even compile all the tests all of the time, but have a bunch of tests with a bunch of different audio files, and maybe that test is compiled by your pipeline, but maybe not on your computer every time you compile. That could be a solution and a way to kind of just test that, maybe a loud sound versus a soft sound, that everything is still working the way you would expect. I think that covers that.
Hi, have you had any problems with targeting different hardware and different processor styles? So it would work for some processors like Intel, but not for others. Have you encountered any problems like that?
That's a great question. As far as Mac, Intel versus Apple Silicon, I didn't really run into any issues, at least not with our code. There are definitely differences with Microsoft MSVC versus Mac. I guess it's kind of par for course. It needs to compile on both platforms if you're targeting both of those platforms. Those are the only platforms we support. Is Mac and Windows for our audio plugins. One example is that I was mentioning earlier that you could you could say a function is Constexpr, but not be 100% sure that it actually is until you try to run it at compile time. So the compilers that you're using may let you get away with more or less. So I've had many instances where I wrote Constexpr on a function and it compiled fine, and then only to find that it broke Windows, because Windows was a little bit more strict about what you label Constexpr. Ultimately, in that case, Windows was right, because it really wasn't Constexpr. It's just Mac was letting me get away with more. The Apple Clang was letting me get away with more. But yeah, that's been my experience.
Hi, yeah, that slide about the differences between compile time and runtime execution was really interesting. But I wanted to know, it sounds like you're running all your tests in C++20.
Yeah, so at the end there, those were all C++20. So because they depended on std is constant evaluated specifically. So C++20 really does unlock a lot that you can do, and that's sort of kind of the point of the talk, is just how far we've come with compile time programming. But as I said, you could make your Constexpr stuff conditionally Constexpr, where maybe over here in one pipeline, maybe that's where you compile it with C++20 and confirm that these tests are successful. But maybe in your actual plugin, maybe you don't use C++20 and that's totally fine. So yeah, there's sort of things you can do to get around that. To not require C++20.
Yeah, because I wanted to ask, have you had to move other code bases to C++20 as a result of that? And have you had any resistances there?
I mean, I've sort of just been moving our plugins to C++20, and we just haven't really had a problem with it. I know that, for people who program for like hardware and stuff like that, I guess, your mileage may vary, but yeah, I just haven't really run into an issue with that, yeah.
Hi, another debugging question.
Okay.
So you can't step through the code, but for example, if you have a Constexpr function that returns a number and you break just before it and step over it, can you see the resulting value, or is it just a black hole in the code?
So like, I have the Constexpr function that I'm statically asserting and making it run at compile time, returning a number, and you're saying, like, do I know what that number is?
Yeah, then in runtime if you break. Or do you see anything in when?
No.
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 Okay.
So I guess, this is for code, this is migrating a legacy code base over to, stricter C++20 Constexpr kind of context. We already knew that the code worked, and now we're just sort of adding safeguards in now. So one way you could do that, I guess, is to have your unit tests already, and then add these in as well, and then that way you know that you're getting the result that you want. But like I said, there is a way you can use templates in your code to like return errors, and then maybe you could abstract those into some kind of crazy macro. I just haven't done that, and then maybe you'd know what the return value is. Is that good? All right. Thank you guys so much. Really appreciate it.